Good afternoon, guys. Hope you're doing well. I wanted to talk about Lab 5, what we have down as Lab Lecture 5, which talks about stoichiometry and the synthesis of calcium carbonate, which is the virtual lab 6. And when we do the synthesis of calcium carbonate in the physical lab, there are some other things that are done that are not done in the virtual lab. So while I understand that you're going to go through the stoichiometry calculations through that experiment, with what you're doing in the virtual lab. Things are a little bit different in the way that we set it up in the physical lab. So I wanted to talk a little bit about those differences. And then I want to talk about that stoichiometry worksheet that you've been given. So I'm going to go ahead and share my screen so that we can talk about a couple of things from D2L that we need to be able to talk about. So lab 5, the gas evolution reaction. This is where we're talking about the experiment from the lab. It's experiment 5, stoichiometry gas evolution reaction. And this talks about how the experiment is actually done. So there are some calculations that are being asked for this, and that's to calculate how much the theoretical yield will be for this particular reaction. And then based on your actual yield and your theoretical yield, you calculate a percent yield. Okay. I wanted to talk a little bit about how this is actually done with some information that we have here. So this is the reaction in sum that's being done. A weak base is added to a strong acid. That weak base in the red is yellow. Okay, so that's why this is listed as yellow. When it is acidified and we add enough acid to it, it changes to the red color. Okay, and that acidification is what causes this reaction. So we need to make sure that we've gotten it acidic enough to make the reaction occur. So that's why we use the indicator to tell us when we've got enough done. Okay, so we go ahead and we add some of that methyl red to it. We add some acid to it, and that solution is acidic. You're then going to put a watch glass over the top of this thing. Okay, that's what you see. There's a watch glass cover here. You've got all of this stuff in acid. So you've got your Na plus and the Br minus and the H plus. There's also some Na2CO3 that's still a solid because it is. And those ions can then come together to give us that material. So as the solution heats up, the carbonic acid breaks down, forms water and carbon dioxide gas, and the pH of the solution will rise. Okay, that is totally normal. pH goes up as we take the acid out of it, so that makes a lot of sense. Okay, the CO2 leaves the solution. We remove that from the steam bath, and we add excess water to react with any of the residual Na2CO3. Okay, we'll then put it back into the steam bath. All right, and then we've got our NaBr, the H2O, and the H plus and the Br minus. Remove the watch glass and rinse, and the contents into a dish, which we then have here. Continue slowly heating it to evaporate the water, and then remove the steam bath. So the idea is that we're going to be collecting that NaBr solid that's formed. Now it's aqueous to begin with, so the Na2CO3 we can remove from that. The NaBr is going to be left in that aqueous form. As long as we take the water away, we can measure that material that's collected, and that would then give us our actual yield. Okay, a couple of things that we have to talk about when we talk about this lab that we haven't really talked about in lecture yet. Okay, we're going to be talking on Friday about concentrations. So on Friday, we'll be talking about molar concentrations. That is introduced here. So a molarity is the number of moles of material per liter. Okay, so it's a molarity. We use big M as the moles per liter. It's just a short way to write it. Spectator ions are species that remain unchanged and appear on both sides of the equation. Net ionic equations show only the chemical species that are involved in the reaction. So if we're looking at this, if I have 2.45 grams of pure sodium carbonate and it's treated with excess hydrochloric acid, we want to be able to calculate how much sodium chloride will theoretically be produced. We do that by converting the grams to moles from the Na2CO3. Convert that to moles. Then we use the molar ratio, 2 moles of NaCl are formed for every mole of Na2CO3 that's consumed. and that molecular weight is 58.5 grams. So the theoretical yield, if I start with 2.545 grams of Na2CO3, is 2.70 grams. Now, if my actual yield is 1.54 grams of sodium chloride, my actual over theoretical times 100 would give me 57%. Okay, so that's the calculation of the percent yield. So that's the kind of calculation that you'll be doing in the virtual lab. You may be asked in the lab final to do any of these calculations. What would your theoretical yield be? What would your, if this is your actual yield, what's your percent yield? Those kinds of calculations may be there, probably will be there. They're supposed to occur enough so that it's not a problem. Okay. We can also calculate the volume of HBr that we need to react with 1 gram of Na2CO3. And this is a little bit different than what we've done before. So we're still going to take and convert from grams to moles. So this conversion right here is in grams to moles. We still know that the molar ratio is 1 mole of Na2CO3 per 2 moles of HBr based on the balanced equation, right? Now here's where the difference comes in. So instead of going from moles to grams, we want to go from moles to liters. And the way that we do that is by using the molarity, the moles per liter. So we divide by the number of moles per liter, and that'll tell me how many liters are required, which I can then convert to milliliters. Okay, so this is another way that we can do this calculation. Remember that I told you that we can go from grams to moles, and then moles of this to moles of that, and from moles of that to all kinds of other things. This is one of those other things that we can do. Okay, so we can deal with going from grams to moles or moles to grams. We can deal with going from molarity to moles and from moles to molarity based on the volume that we have. Eventually, we'll do some other calculations that come on. Okay, we can calculate a theoretical yield here. Right? And of course, that's slightly different. So this is how much NABR was required to do this reaction. Now, if we calculate a theoretical yield based on this, we get the 1.94 grams of NABR should be produced. Okay, so that's no different than what we talked about before. Now, remember, when we talk about net ionic equations, we know that we're going to get rid of anything that doesn't appear in the final reaction. Okay, so if we want to talk about the net ionic equation to make that NABR solid, right, we want the Na plus the Br minus and the NABR. Now, if we want to talk about the net ionic equation to get the formation of CO2 and H2O, that's a slightly different reaction. So we talked about this, today in class, and I said that there may be multiple things going on that we want to look at. They're two completely separate processes. And so we can talk about them in different ways by splitting those anionic reactions to do that. That allows us to talk about the chemistry that's involved in each one separately. Okay, so that's part of what we're talking about there. So you should be familiar with the equations that are there. You should be able to calculate a theoretical yield. You should be able to calculate how much of the acid you need in a calculation similar to this. So how much of this acid is needed to perform this. We've done that calculation before, calculate a theoretical yield, calculate a percent yield based on a theoretical and an actual, all of those calculations. And all of those calculations go directly into stoichiometry, okay? We talk about stoichiometry. We know that a limiting reactant is the thing that limits how much product I can make. So when I do this reaction, there's a fixed amount of A that I need for a fixed amount of B. And if I don't have that ratio, if they're not in the right proportions, I can't convert all of it. So I usually have one that's left over. Okay, the one that's left over is not the limiting reactant. The one that's completely consumed is the limiting reactant. Okay, so it's the one that's totally consumed and runs out first. Okay. Potential example, hot dogs with buns and franks. Okay, we've talked about this before. So I can only make 8 hot dogs with buns and franks if I buy an 8-pack of hot dogs and, or if I have an 8-pack of buns and 10 hot dogs. Okay, so all I can make is 8 because I don't have enough hot dogs.
Read your text message. I can't do it.
Now remember that our theoretical yield, again, and this is, we're going to define this over and over and over and over again because we use it all the time. Pretty much, if you're in the physical laboratory, you would be calculating the percent yield from here on out. So this is something that we do a lot. All right, so actual yield over theoretical yield times 100. All right. When we talk about acid-base reactions, we're talking about adding that acid to that base. Remember, we take the H from the acid and the OH from the base to form H2O, and we get a salt. In addition to that, when we're talking about this kind of acid base, sometimes we get that gas evolution that comes with this. And so we need to review how we do those calculations. So there are a number of things that we do in solving a stoichiometry problem. Now, I have to have a balanced equation. That is the first thing I need. Because if I don't have a balanced equation, I don't know what the ratio between the moles of what I have and the moles of whatever it is I'm looking for, whether it be another reactant or a product, I don't know what that ratio is. And so I don't know how to do that, okay? We also need to make sure that we've read the question, and you'll hear me say this, RTFQ. Read the full question. Make sure that you're answering the question that was asked. Okay, so you need to know what you have and what you don't have. All right. When I do this, again, it's very similar to what you see here. I write this N2, I write the H2, I write the NH3. I'm looking for how much NH3 is made from this amount of N2. So I have an amount of N2 that was given to me, and I'm looking for this. When I do this, I put my molecular weights underneath, okay, and now I have all the information that I need right there with my balanced equation. So I'm always referring back to that balanced equation to remind me that I need it. Okay, it's important. I have always had a balanced equation, and I put my data with it so that I remember that I need that balanced equation. Okay, so you're going to be doing a series of stoichiometric calculations. The post-lab for the stoichiometry, when you do this in ALEKS, okay, you're going to be doing exactly these calculations. Do it on paper first, okay? This piece of paper should be turned in. There's a place in the assignments for you to turn this in. Post-lab stoichiometry, okay, that's where that goes. Do it on paper first, and then the answers are going to be put into ALEKS, okay? So how many moles of ammonia, right? And all of these things are some part of that stoichiometry. Now, we may not be going from grams to moles to moles to grams. We may be going from moles to moles. We may be going from grams to moles. There's a number of different parts that we can do with this. So make sure you're reading the question, okay? Also verify that your equation is balanced. Now, it should be, but make sure that it is. Also, make sure that you've used the data that is here so that ALEKS won't freak out about the numbers that you're reporting. Right? I think that's everything I had to talk to you about this. This should be fairly straightforward. If it's not, if you have any questions, comments, problems, anything whatsoever, let me know. This practice is good for you to be able to move on, because even though we're, technically that was a test one thing, what you'll find is that chemistry builds. So everything that we've done so far is going to be required to do the stuff that we're going to. So all of the stuff that we're going to do for test 2 and test 3 is going to require stuff from test 1. Okay, it's just the nature of what we're doing. So don't think that it's disappeared yet. Okay, I think that's everything. So I'm going to go ahead and stop this. I will stop sharing, and I will talk to you guys soon. Thanks.